Power is such an important parameter in the biomechanics and exercise physiology world. And so measuring power becomes an important part of a biomechanical analysis, or if you're looking at physiology. So we have some specific tools in the laboratory that are very useful for measuring power in the laboratory. The trick is making those same instruments behave and measure things correctly out in the real world. So pushing the lab out into the real world it's always a little bit challenging. However, with the miniaturization of instruments and the more availability of wearable technology, being able to measure power has become much more commonplace out in the real lab, out in the real world, the real lab, out in the real world. And athletes have a lot of questions about how to use power to help them train for an event, as well as how to manage effort during an event. So let's talk about measuring power in the lab and in the real world. Well, let's define power to begin with. Power is how fast work is being done. Work is applying a force over some distance. Another way, if you look up in a physics textbook, it may just say power is the rate of work done. Perfectly fine, same thing. Conceptually, power represents how fast energy is being transformed from one form of energy to another form of energy. I always use the light bulb to explain this. We have a 30-watt light bulb, and what that power of 30 watts tells us is how fast electrical energy is being transformed to light energy. A 30-watt light bulb is not as bright as a 100 watt light bulb. A 100 watt light bulb is obviously brighter than a 30-watt light bulb. A 100-watt light bulb is transforming the electrical energy faster than a 30-watt light bulb from electrical energy to light energy. And there's all other forms of transforming energy, and how fast we're transforming energy from one form to another is, in essence, power. In the human body, what we're often interested in is how fast we transform chemical potential energy to mechanical energy. Chemical potential energy would be in, for example, ATP, or we can even backstep that a little further and say potential energy in carbohydrates or in fats as fuel. And our body uses those fuels and has specific metabolic processes to yield ATP, which is then used to shorten muscle in the sliding filament theory of muscle contraction. And ultimately, we have mechanical energy. So we're transforming potential chemical energy, carbohydrates, fats, to mechanical energy, the shortening of a sarcomere and contraction of a muscle. So we often want to know how fast we're transforming that chemical energy to mechanical energy. And we hear terms like aerobic power and anaerobic power. Those are terms that we use in the exercise physiology world to represent how fast we're transforming chemical energy to mechanical energy aerobically and anaerobically. Okay, I digress a bit there. Equation for power is work over time, rate of work done, or another way to describe the equation for power is its force times velocity, or how fast a force is being applied. And work, remember, is force times distance. Distance over time is velocity. So this equation and this equation are exactly the same equation. We just rearrange some of the parameters. In either way that we calculate power, we use the units of watts. Okay. All right. So now, how do we measure? In the laboratory, we actually do a lot of measurement in gait or in jumping or landing from movements using a force platform. You may have used one of these in your undergrad biomechanics laboratory experience. It is in essence a glorified bathroom scale. It measures the ground reaction force in 3 dimensions, and then we can use that information to ultimately calculate power because we figure out how fast that force is being applied. So that's running in the lab. This force platform right here, $20,000. And we can't put this force platform outside to get more than one step at a time. We can put it outside, but we get one step, one foot contact at a time. Doesn't really make a sense to put this out in a marathon. For example, we would need far too many force platforms, each one costing about $20,000. We could also, in the lab, use a cycle ergometer, and this is just one example of one. It has a power meter in it, and you can control it. Obviously, it doesn't have a front wheel, whereas some cycle ergometers only have a front wheel, and they actually reverse this chain, so it actually moves the wheel in the front as opposed to having something on the back. In essence, this is a mechanically instrumented device where we can measure power during cycling very accurately and easily in the lab. But to move this outside, actually it has become much more commonplace. I'll talk about that in just a second. And then in the laboratory, we could use a swim ergometer. And this is a picture of a swim ergometer here. This is the Vasotrainer. This is the device up here. There's actually hand paddles right here that the swimmer would lie on this bench facing this unit right here, grab those hand paddles, and then this instrument here is measuring power. So good ways to do power measurement in the laboratory, but these are not easy devices to move outside. Maybe the bike has become easiest. So let's talk about measuring power in the real world, where an athlete can do their swim in open water or in a pool versus on a dry land swim trainer, or the biker, the cyclist can bike outside or run outside. Different techniques for measuring power out in the real world is the MAD system. I've got some videos on this. This is this system right here. This is a measurement. This is in essence a force platform in the water, and there's a series of them, 16 of them in this system, where the swimmer swims along and pushes on that force platform, and we're able to measure the force acting on the hand, which in essence is the propulsion force. This is great, but we're limited to, in essence, a 25-yard pool and still a lot of technology. You can't have this along a 2.4-mile swim like an Ironman, but really neat to be able to measure this while actually swimming in a pool. This is a new system right here, and this company that actually I used the picture from is no longer in business. They actually got bought out by another company. This is a force measuring device that's put in the palm of the hand. And you're measuring force at the hand here by measuring pressure, which actually you can get force when you know pressure is force per unit area. And if you know the area that this pressure sensor is measuring, you can now derive force from that. Still a little bit tricky, and yet I believe this is going to be the next wave of swim technology that is really going to become popular, because now you're able to get some sense of force while measuring. I've tested out a couple of these devices. They worked okay, but I think each iteration of the device and development of the device, eventually this will be a device that will be useful for swimming anywhere, open water, in a pool, what have you, because now it is fully portable. You can also devise a tether system where you're in a pool and the swimmer wears a tether around their waist, and that tether is connected to a measurement device that's on the deck of a pool. That's a nice sort of example of doing this, but yet you still can't use that device out in open water. So it's just a little tricky in swimming to actually measure power. I think this hand device is going to be the most successful ultimately to be able to be measuring power while swimming out in the real world. Biking power meters have become very common in bikes. You have bike power meters in the rear hub of the bike. You also have power meters in the hub of the crank system, as well as power meters on the crank. Those are three ways that power meters are integrated into bikes. And very popular for athletes to be using a power meter while biking and getting some power data. I'll have some other videos where we actually look at power during biking. This has become a very easy way to measure power out in the real world. There are some tricks with understanding what this power means. And, uh, and there are some ways to accidentally get this information confused with physiological power. The whole idea of measuring these mechanical power works when the athlete is primarily sitting in the seat. When the athlete comes up out of the seat, we have transformation of power from a mechanical to mechanical. Mechanical in terms of potential energy to mechanical of movement, moving the actual pedals. And that sort of takes away from our use of this device to understand physiological power. Finally, with running, this has also been a bit of a trick, just like swimming. It's not easy to get running power. However, there are becoming more devices that are getting close to developing an algorithm to yield power while running. You put these devices on your shoe and then you run outdoors. The trick is when you're running up hills or running down hills or when you take a step off a curb or what have you, those changes are not easy to account for when you're actually calculating power. If I go back to this situation, this platform is perfectly level, it's not moving, and we can actually determine power quite easily from this type of device. When you're running up hills, maybe changing directions, that gets a little bit trickier. We do have some insoles that we can put inside shoes, and that is actually another layer of instruments I don't have pictured here that is useful out in the real world. However, on a limited basis, because those insoles only last so long, and then they actually start to degrade in terms of performance. All right, so this is where our goal is with trying to measure out in the real world for not only research purposes, but also for user purposes. Because if the user can get more information back in terms of the mechanics that they are using to swim, bike, or run, hopefully that will translate into designing better, more effective training programs, as well as trying to help an athlete pace during a specific event. Okay, I hope that's helpful. Thank you.